So this is question number 27 of GATE 2020 Metallurgical Engineering. Which of the following dislocation reaction is not feasible in a FCC crystal? Right. So we have to find the non-feasible reaction in an FCC crystal. So you can also refer NPTEL course on structure of materials by Professor Anand Subramaniam to know more about the dislocation reaction in different types of crystal system, right? So let us first understand some basics about the dislocation reaction, its feasibility, possibility. Now, this energy of a dislocation, if you see, is given by, like, it will be approximately equal to 1 upon 2 of GB square, where B is our Berger vector and G is the shear modulus. So for a given dislocation, all the dislocation will wants to have as minimum energy as possible. So in order to achieve that, the value of B, they wants to keep it as minimum as possible. So dislocation will have as small a B as possible. So they will minimize the value of B, Berger vector, in order to have a minimum energy so that they can be stable, right? And sometime what happen, dislocations may dissociate into partial dislocation to reduce their energy. So they will like one dislocation will be split into two, but the final destination, like if it is moving, will be same. The vectorial sum will be same of the two partially splitted dislocation. But if you see the energy balance, it will be reduced energy after the splitting. And also they may split into Shockley partial. So the splitted dislocation will be known as Shockley partial to reduce their energy. So by doing so, they will be basically reducing their strain energy, right? Now let's have a look on the FCC crystal and dissociation of dislocation. So let's say we have a dislocation with Berger vector in this red color, right? B1. So this is our B1, and it is moving from this point to this point. So this dislocation B1 is moving from this location to this location. So rather than going directly from this to this point, it can also split into two partials by moving from this location to this and then again from here to here. So final destination will be same, and also this vectorial sum of this B2 with Berger vector B2, and this is our another dislocation with Berger vector B3. So the vectorial sum of B2 plus B3 will be equal to B1, but the energy should be such that the final energy after splitting should be less than the initial energy, right? So the energy we just now saw is related to the square of Berger vector. So if you take the square of Berger vector with their magnitude, it will be this B1 magnitude square will be greater than B2 magnitude square plus B3 magnitude square, right? So this is the condition for a favorable dislocation reaction. So in order to split the dislocation into two partials, this condition must satisfy. So we'll see one by one all the options whether this condition is satisfying or not. So the option is 1 upon 2 0 1 1 direction. So first we'll check the vectorial sum, whether these two sum are equal to this or not. If it is not, then it's not a feasible reaction. See the vectorial sum. So on LHS left hand side we have 1 upon 2 0 1 1 direction, and on RHS we have this plus this. So simply summing it, 1 upon 6 upon 1 plus 1 bar will give you 0, 2 bar plus 1 bar will give you 3 bar, and 1 plus 2 will give you 3. So if you simplify it, it will be equal to 1 upon 2, 0, 1 bar, 1. So the vectorial sum is correct. Now if you see the energy balance, so the magnitude of B1 square will be equal to 1 upon 2 under root 0 square plus 1 bar square plus 1 square to the whole square. So it will be equal to 1 upon 4 times 2, which will be equal to 1 upon 2. So we got the B1 value, magnitude of B1 square value. Similarly, we will calculate the B2 magnitude, which is this B1. This is our B2, this is our B3, this is our B1. Assume that these are 3 Berger vectors, right? So B2 magnitude square, if you calculate, it will be equal to 1 upon 6 under root of 1 square plus 2 square, 2 bar square plus 1 square to the whole square, right? So you will get 1 upon 36 times 6, which will be equal to 1 upon 6. Similarly, you will get B3 magnitude square will be equal to 1 upon 6. So if you calculate B2 plus magnitude of B2 square plus magnitude of B3 square, you will get 1 upon 6 plus 1 upon 6. So simply it will be equal to 1 upon 3. So now you can easily see 1 upon 2 is greater than 1 upon 3, which means by splitting we are reducing the energy of dislocation. So option A is feasible, right? Possible reaction, right? So option A is true. Similarly, we will check option B. If you see option B, so let's first have a look on vectorial sum. So 1 plus 1 equals to 2, 1 bar is 2 bar, 0 0 is 0, so upon 2. So it will basically give you 1 bar 0. So this is what we are getting at the right hand side. So vectorial sum is correct for this option. If you see the vectorial sum, we will get 1 upon 6 times 1 plus 2 will give you 3, 1 plus 2 will give you 3, and 2 bar plus 2 will give you 0. So if you equate this, we will get 1 upon 2, 1 bar 1 1 0. So this is what we are getting this right side. Similarly, this option, you will, if you sum this, we should get this. So 1 upon, if you sum this, 1 upon 6, 2 bar, 1 bar is 3 bar, 1 plus 1 bar will give you 0, and 1 plus 2 will give you 3. So if you simplify, we will get 1 upon 2, 1 bar 0 1. So vectorial sum is correct. So only thing is we need to check the energy of left hand side and right hand side. So the option B, if you check the energy balance, left hand side we are getting energy 1 upon 2 under root 1 plus 1 bar square plus 0 to the whole square plus 1 upon 2 under root 1 plus 1 bar 1 square plus 1 bar square plus 0, right, to the whole square. So it will be equal to 1 upon 4 times 2, and similarly 1 upon 4 times 2, right? So it will be equal to 1. And if you see the right hand side, it's simply under root of 1 square plus 1 bar square plus 0 square to the whole square. So it will be equal to 2. So the LHS, left hand side, LHS is less than RHS, right? So by this reaction basically our energy is increasing, so the option B is not feasible, right? Because we are increasing the energy, which should not be happen. So the option B is not feasible. We will check other option as well. Option C, if you have a look, we'll have LHS equal to 1 upon 6 under root 1 plus 1 plus 2 bar to the whole square will give you 4, and 2 whole square plus 1 upon 3 times under root 1 square plus 1 square plus 1 square to the whole square. So it will be equal to 1 upon 36 into 6 plus 1 upon 9 into 3. So simply it will be 1 plus 6 upon 1 plus 3, which will be equal to 3 upon 6, right? And that is 1 upon 2. So LHS we got 1 upon 2, right? And if you see the RHS will be 1 by 2 under root 1 square will 1 square will give you 1, and 0 square will give you 0, and to the whole square. So it will be equal to 1 upon 4 into 2 is equal to 1 upon 2. So LHS is equal to RHS. So in this case we have a balance, so it's a feasible one, right? Basically an equilibrium condition. Option D, if you check, we'll have 1 upon 2 under root 1 bar square will give 1, 0 square will give you 0, and 1 square will give you 1 to the whole square. This is our LHS. So it's equal to 1 upon 4 into 2, that is 1 by 2. And RHS, if you see, 1 upon 6 square, this will give you 36 into under root of 2 bar square is 4, 1 square is 1, and 1 square is 1, plus 1 upon 36, 1 bar square is 1, 1 bar square is 1, and 2 square is 4. So, and also this whole square and this whole square. Already I did 1 upon 6 square, that is 36, so only I am doing this whole square. So it will be 1 upon 36 times 6 plus 1 upon 36 times 6, so which will give you 1 upon 3. So LHS here also is greater than RHS, so this is also a feasible reaction. So option A was feasible, option B was not feasible, option C was equilibrium condition, like it can be possible in either way, forward or backward, and option D is basically feasible. So the not feasible condition is option B. So the right answer for this question will be option B. Thank you.